Right now, as you're reading this, something 26,000 light years from Earth is detonating. Not occasionally, not sporadically. It's exploding constantly, every single day, without rest, without warning, and without anything resembling a pattern. For half a century, astronomers told us a reassuring story about the black hole anchoring our galaxy. They said it was peaceful. They said it was ancient and essentially dormant. New observations have now shattered that comfortable narrative. And the researchers who collected the data confess they're still scrambling to interpret what they've witnessed. Let's explore what the Milky Way's core actually looks like now that we have the technology to see it properly. For years, Sagittarius A had a reputation for being boring. Compared to the cosmic monsters out there, our black hole seemed almost sleepy. Take the one in galaxy M87, about 53 million light years away. That beast is roughly 600 times more massive than ours, surrounded by a brilliant accretion disk, shooting plasma jets that extend for thousands of light years. Next to something like that, our galactic center looked starved, dim, and half asleep. That was the conventional wisdom for decades, and honestly, the evidence appeared to confirm it. Sagittarius A doesn't shred stars weakly. It doesn't shine anywhere near as brightly as its relatives. So when astronomers finally secured the longest, most detailed observation period ever, practically nobody predicted what they'd find. Before we examine the discovery, we need to understand what actually lives at our galaxy's center. Without that context, nothing that follows will make sense. Sagittarius A sits approximately 26,000 light years from Earth, in the direction of its namesake constellation. It contains roughly 4 million times the mass of our Sun, and all that mass is squashed into a region only about 15 million miles across. To grasp that scale, consider this. That's about 1/6 of the distance from Earth to the Sun. Imagine taking everything orbiting our star, every planet, every asteroid, every dust particle, multiplying that by roughly 4 million, then compressing it all into a ball smaller than Mercury's orbit. That's what's sitting at the center of the galaxy you call home. What that mass does to space and time is almost impossible to visualize. Near the black hole, time literally runs slower than it does out here. A clock at the edge of Sagittarius A would tick noticeably slower than the one on your wall. Light bends into strange curves and spirals as it passes close by. An object behind the black hole can have its light warped around the event horizon like a ghostly mirage. That exact effect appeared in the first image of Sagittarius A, released in 2022. Light from the far side of the glowing disk had been dragged almost completely around the black hole before finally reaching our telescopes. The event horizon, the actual point of no return, sits about 7 million miles from the center. Cross that boundary and you're gone. No light comes back, no matter comes back, no information comes back. We can never see the horizon directly because, by definition, nothing that crosses it ever returns to tell us what's there. All we can observe is the behavior of everything trapped in orbit around it. Here's something to sit with for a moment. Tonight, if you look toward Sagittarius, you're looking straight at this object. You can't see it with your eyes because thick dust between us and the galactic center blocks almost all visible light. But the radiation from its flares is arriving on Earth right now. Light that departed the black hole's vicinity long before recorded history began. We know how violent the environment around Sagittarius A is because of the stars caught in its gravitational grip. One star, called S2, traces a 16-year elliptical orbit, swinging as close as roughly 11 billion miles before hurtling back into darkness. At its nearest approach, S2 moves at over 17 million miles per hour. A rifle bullet travels at about 800 miles per hour. That means S2 at its peak is roughly 10,000 times faster than a bullet, and it's not even the speed champion. Other stars in the inner cluster have been clocked at over 8% of light speed. How did we even figure out something invisible was there? It began with radio waves. In the 1970s, astronomers detected a strange compact source of radio emission from the galactic core. By the 1990s, 2 independent teams began tracking individual stars near that source, watching year after year as those stars whipped around something they couldn't see. The mathematics left no other conclusion. To bend stars into orbits that tight and that fast, whatever sat at the center had to weigh about 4 million suns, all crushed into a region smaller than Pluto's orbit. Only a supermassive black hole could explain it. 2 researchers behind that discovery, Reinhard Genzel and Andrea Ghez, received the Nobel Prize in Physics in 2020. They never saw the black hole directly. They proved it existed by observing its effect on everything nearby. Then in May 2022, after decades of work, the Event Horizon Telescope team released the first direct image of Sagittarius A. It showed a glowing orange ring around a dark void. Gas, heated to millions of degrees, illuminated the ring, while the event horizon's shadow sat black in the center. To grasp how hard that photo was to capture, imagine standing in one city trying to photograph a donut sitting on the moon's surface. That's roughly the angular size of Sagittarius A warrant from Earth. The team accomplished it by linking radio dishes across multiple continents into one virtual telescope, effectively turning the entire planet into a single lens. Data from the South Pole Station was so massive it had to be physically transported on hard drives rather than sent over the internet. Then it took roughly 5 years of computer processing to transform that raw data into one final image. That image was a monumental achievement. It was also just a single frozen frame, a snapshot of something that never actually stays still. To see what Sagittarius A really does, you need a telescope that can stare at it continuously, using light that penetrates the dust with enough clarity to track activity inside the glowing disk in real time. Only one instrument could handle that job. The James Webb Space Telescope launched on Christmas Day 2021. It orbits the Sun about 1 million miles from Earth at a stable point called L2, cold enough to keep its mirrors sharp and infrared. Infrared light cuts straight through the dust, hiding the galactic center. That means Webb, more than any telescope before it, could finally look directly at something that had been concealed from human eyes for our entire species' existence. Astrophysicist Farhad Yousefzadeh from Northwestern University led a team that used Webb's near-infrared camera across 2023 and 2024 to attempt something never tried before. They aimed the telescope at Sagittarius A for a total of 48 hours, broken into stretches of roughly 8 to 10 hours, spread across a year. Their goal was almost absurdly simple. Just watch. Keep watching. See what the galaxy's central black hole actually does when no one's forcing it to behave. From the very first session, the black hole was doing something unexpected. The glowing ring of superheated gas, the accretion disk, was flickering constantly. No calm periods, no predictable rhythm, just restless, relentless brightness the entire time Webb was watching. Yousefzadeh later described it as constant bubbling, never settling into anything stable. On average, the disk produced 5 to 6 major flares daily. Between those larger bursts, smaller flickers appeared and vanished in seconds. Some of the faintest flickers, barely above background noise, seemed to smolder quietly for months. Every observing run revealed something new, different patterns, different brightness levels, different combinations of bright flashes and dim glow. Yousefzadeh admitted the team expected occasional flares. That's normal for supermassive black holes. What they didn't expect was that there would never be a quiet moment. Sagittarius A, it turns out, doesn't really produce individual flares the way we thought. It's more accurate to say the entire disk is one continuous flare. Now, what we call flares are really just the brightest peaks inside a storm that never actually ends. Picture this. A dim ember glowing faintly at center, surrounded by a soft haze. Every few minutes, somewhere inside that haze, a hot spot suddenly brightens, then fades. Sometimes a larger pulse rises from the background glow, holds for several minutes, then collapses. Sometimes a small flicker just sits there steady for an entire observing session, refusing to change. Compress 9 hours of that footage into 30 seconds. The team actually did this and released it publicly, and the result looks unsettlingly alive. It doesn't resemble a stable gravitational anchor. It looks like something breathing. No one could find a pattern anywhere. Not on the scale of seconds, not on the scale of hours. The bursts happened when they happened, where they happened, at whatever brightness they reached. And that randomness is itself significant. If the chaos doesn't follow some clean, repeating cycle, then something more complex is driving it from deep inside the disk. The last 2 years have added even more pieces to this puzzle. In April 2024, another team used a different Webb instrument, the mid-infrared instrument called MIRI, and captured something never recorded before, a full flare from Sagittarius A in mid-infrared light. That part of the spectrum is invisible from the ground because Earth's atmosphere blocks it almost entirely. The only way to see mid-infrared light from 26,000 light-years away is from space. That day, Webb recorded a roughly 40-minute outburst. A team led by Sebastiano von Fellenberg at the Max Planck Institute in Germany modeled the event and found the clearest evidence yet for magnetic reconnection inside the accretion disk. Magnetic field lines twist and tangle as plasma spirals inward. When the tension becomes too great, the field lines snap, releasing enormous energy and flinging charged particles outward at near light speed. Then in 2026, another instrument added a fresh twist. Astronomers using the ALMA Radio Observatory in Chile found clear evidence that Sagittarius A blows out a steady wind, material pushed away from the black hole rather than falling in. That's a discovery scientists had been chasing for over 50 years. Around the same time, Chandra X-ray Observatory data confirmed that this hot outflow has been quietly shaping surrounding gas for a long time. And most surprisingly, data from the newer X-RISM Space Telescope suggests that sometime within the last few hundred to 1,000 years, Sagittarius A actually flared far more dramatically than anything recorded in modern observations, based on X-ray light still echoing off nearby gas clouds. In other words, the version of the black hole we're watching today, restless and constantly flickering, might actually be the calm phase compared to what it was doing just a few centuries ago. Put all this together and you get a very different picture of our galactic center. It isn't just flickering randomly. It's blowing wind outward, snapping magnetic fields apart, echoing with the aftermath of a much larger outburst from the recent past, and doing all of it constantly, whether anyone's watching or not. The wind discovery deserves extra attention because of how long scientists had been searching for it. For half a century, researchers suspected that black holes like ours had to push some material away, while pulling other material in, simply because the numbers never balanced without it. Gas falls toward the black hole from every direction, but only a tiny fraction actually crosses the event horizon. The rest has to go somewhere. ALMA's 2026 findings finally gave scientists a direct look at that missing piece. A steady outward wind carrying material away. Chandra's long-term monitoring lined up with this picture, showing a hot outflow that appears to have been reshaping gas near the galactic center for a very long time. Instead of a black hole passively waiting for material to fall in, the new picture is closer to something constantly pushing and pulling at once, inhaling and exhaling in the same breath. Then there's the XRESM result, perhaps the strangest piece of all. By studying how X-ray light bounces and echoes off nearby gas clouds, scientists worked backward to estimate that Sagittarius A Auric produced a major outburst sometime within roughly the last few hundred to 1,000 years. A flare far larger than anything caught by modern instruments. Gas clouds near the galactic center absorb radiation from such an event and slowly remit it over centuries, acting like a delayed echo chamber. Reading that echo lets astronomers reconstruct outbursts that happened long before any telescope existed. If this finding holds, it means the constant flickering Webb has recorded over the last 2 years, as dramatic as it looks, may actually be Sagittarius A on one of its calmer stretches. Whatever happened a few centuries ago was, by comparison, on another scale entirely. One particular measurement from the original 48-hour Webb campaign turned out to matter more than almost anything else. Yusufzadeh's team observed the black hole simultaneously at 2 different infrared wavelengths. 2, 1 microns, and 4, 8 microns. Every time a flare occurred, the shorter wavelength brightened first. The longer wavelength always followed, lagging by anywhere from a few seconds up to about 40 seconds. That delay might sound like a minor technical detail, but it's actually the most important single measurement in the whole data set. It works like a fingerprint. Shorter wavelengths come from particles carrying more energy. As those particles lose energy over time, they start emitting light at longer and longer wavelengths. Watching a flare shift from short wavelength to long wavelength is like watching in almost real time a group of particles that had just been violently accelerated to near light speed gradually cool down. Scientists call this process synchrotron cooling. Before Webb, nobody had ever directly measured it happening around our own galaxy's black hole. What that actually means is almost hard to process. We're watching nearly real-time particles being flung outward from the edge of a region where normal physics starts breaking down. Some flares point in random directions. A small number, purely by statistics, must point roughly toward Earth. At 26,000 light-years, that radiation is far too diluted to pose any danger. But every time you watch footage of Sagittarius A flaring, a fraction of that light is energy generated at the boundary of a black hole. Energy that has been traveling through interstellar emptiness for 26,000 years, just now landing in the mirrors of a telescope parked 1 million miles from Earth. We're not looking at ancient history in the abstract. We're looking at events that were unfolding at our galaxy's center while early humans painted on cave walls. Here's the part that deserves more attention than it usually gets. Sagittarius A is not the most violent supermassive black hole out there, not even close. By almost every objective measurement, it ranks among the quieter ones. M87's black hole is 1,600 times heavier, wrapped in a denser disk, and regularly launches plasma jets stretching thousands of light years. Elsewhere in the universe, quasars powered by central black holes outshine their entire host galaxies combined. Compared to monsters like those, our galactic center looks practically asleep. And that's exactly what makes the new data unsettling. Even the boring one, the black hole we spent decades dismissing as calm and uneventful, has an accretion disk that never settles down, blows outward wind, snaps magnetic fields apart in violent bursts, and shows fingerprints of a much bigger outburst sometime in the last 1,000 years. On average, something 15 million miles across is exploding brightly enough to be detected across 26,000 light-years of dust roughly 6 times a day. It has been doing this for billions of years, completely unnoticed, completely unrecorded, until the last couple of years finally gave us the right tools to watch. There's still a major piece of this puzzle scientists haven't solved. Based on current models, the amount of gas actually falling into Sagittarius A isn't enough to account for the activity Webb is recording. Something appears to be feeding the disk more steadily or more violently than existing models predict. Maybe it's stellar wind from stars in the surrounding cluster. Maybe it's a slow ongoing tidal disruption nobody has properly accounted for yet. or some combination of the newly discovered outflow and old or unseen sources of material. Yusuf Zaydeh's team is now hoping to secure a full 24 uninterrupted hours of observation time to hunt for finer structure hidden inside all that chaos. In a very real sense, the science is still racing to catch up with what the telescopes have already shown us. Take a moment and actually picture what's sitting at the center of the galaxy you live in. A region about 15 million miles wide, holding the crushed mass of 4 million suns. An event horizon with a radius of roughly 7 million miles. A disk of plasma heated to millions of degrees, spinning at speeds close to light speed, being torn apart over and over by its own tangled magnetic fields, throwing bursts of high-energy radiation outward in every direction, hour after hour. Stars nearby being slung around at a meaningful fraction of light speed. And every single star in the Milky Way, including the one lighting your sky right now, locked into one enormous slow orbit around that same chaotic point. Our sun takes roughly 230 million years to complete a single lap around Sagittarius A1. Since Earth first formed, we've made only about 20 of those laps. There's something genuinely humbling about realizing the object holding your entire galaxy together isn't the stable, quiet anchor we were taught to picture in school. We grew up imagining the Milky Way as a giant spinning wheel of stars held in shape by one simple silent mass at the center. The newest observations make it clear that Anchor is anything but silent. It's a 4 million solar mass storm of restless, tangled physics sitting at the gravitational heart of roughly 200 billion stars, still doing things scientists who study it for a living can't fully explain. We tend to imagine black holes as movie monsters or strange curiosities in distant galaxies far removed from anything that touches our lives. But the one holding our own galaxy together, the one keeping every star in the Milky Way, including our sun, locked in its slow orbit, is right now, while you're reading this, throwing bursts of radiation out into the darkness. It was doing exactly this while the pyramids were being built. It was doing this while the first humans were walking across Africa for the very first time. And it will still be doing this long after everyone reading this today is gone. 26,000 light years away in a place we will never physically reach, the center of the Milky Way keeps pulsing with light that we have only just learned how to see. And every one of us is slowly spiraling around it, along with everything else in this galaxy. Thanks for watching, and I'll see you in the next one.